Hello everyone. I want to talk today about building a programming language. And as these are typically implemented using trees, um, I figured why not be among the trees, right? So let me get started by saying you should probably not build a programming language, at least not for real, because it's a lot of work. There's so many things that you need to do. You need to think about parsing the programming language. You need to think about evaluating the programming language. You need to think about documentation. You need to think about building an ecosystem. You need to think about errors. When you parse, when you evaluate other errors, you maybe need to build a type checker. And there are so many things. It's a huge task. And even if you do all those successfully, there's a big chance that your programming language might fail. So those are all reasons why not to build a language. So you might ask, why am I giving this talk? Well, there are some good reasons to build a programming language. And first of all, I think it's a lot of fun. There's some really beautiful code that you can write, and you'll learn a lot. And worst case, you'll learn at least better how the programming languages are built and how you can work with, for example, a compiler or a different language. So these are some reasons why you would want to do this. And now, building a programming language, or what we will look at today, is an implementation for an interpreted language, and we'll implement it in two phases. So the first phase is parsing, which means we take a string and we try to turn that into a parsed tree of expressions. And then the second phase is we evaluate that parsed tree down to a value. And the language I chose for today is a simple templating language. It has HTML. It's an HTML templating language, and it has support for tags, of course, HTML tags, strings, integers. It has functions and function calls, and it has variable definitions. And it's a minimal fantasy language. I'm absolutely no expert on how to build a programming language, but I still wanted to show you that you can get very far without being an expert and without having to use any complicated tools. That said, let's look at the first step, and that's parsing. When we want to parse a programming language, there are, again, many different techniques that you can use. And you can use, for example, parser generators. So those are tools that you give a grammar, and then they take that grammar and write code for you. So it basically generates a parser for you. That's why it's called a parser generator. Then there are parser combinators, which are typically implemented as a library. So you would import this library and write your parser using these combinators. So this comes from functional programming. But you don't need all of that. If you just want to write your first parser and want to learn about this, you can actually just use plain Swift and strings. Now, what a parser does is it takes a string and it builds a tree. And it does that by removing parts of the string, typically from the start of the string. And we could make our parser work with strings and just, like take a string as the input and then get small pieces of that string and parse the rest of the string and so on. But this approach very quickly breaks. And the reason is performance, because if you copy strings around all the time, it gets very expensive. And what we'll do instead is use a substring. So a substring is basically a string with an index. And as you remove parts of the substring, that index moves. So the original string stays alive. So that means that we can very efficiently write parsers. The only thing that changes is this integer. So there's not much copying that needs to be done and not much mutation. It's all fairly cheap. So let's get started. So I'll show the little language we have. So it supports things like variables. So if we type x, we want there to be a variable that's parsed. It supports numbers like 42. If we parse this, we expect an integer of 42. It supports things like strings, where we type a string literal, and it gets parsed as a string literal hello. And it supports things like let expressions. So here we can say let x equals 5 in, and then the body of the expression. So maybe we say x, for example. And this gets parsed as a tree structure. So here we have a let, and it has two branches. So one branch is for the value of the variable. So here we say let x, so that's the value of x. And then the other branch is for the body. So within that body, you can use the variable x. Our language supports tags, so we can do something like p and closing p. And of course, if something goes wrong, so if we forget to close the tag, or words we forget to forget an angle bracket, then of course we do expect errors from our language. And it supports function calls, so you can do something like foo and call it, and pass in parameters, maybe 42 and a string, and all kinds of expressions. And this gets parsed again as a tree, where we have a variable foo as the left-hand side of the call expression, and then it has two parameters, and that's the int 42 and the string hello. Let's look at the code you need to do to write to do this. So the first thing is we need to define what our expression type looks like. And we can represent it as a simple enum, or actually maybe not so simple. It's an indirect enum, which means we can represent trees and we can use expression within itself. So it's an indirect enum, and one of the simplest cases is for a variable, and that just contains the name of the variable as a string. The next case is integer literals, and that simply contains the number as an integer. And string literals are again very simple. They contain the string that's represented. Now when we write a function, it gets more interesting. So a function has a list of parameters as strings, and then it has a body, which is again an expression. So you can already see that this is a recursive definition. So within a function, we can now have variables or integer literals or string literals, or even more functions. And then we have a call expression where we have a left-hand side. So typically that's a variable, but it could be something else. Maybe at some point we allow member expressions so that you can say a.b, for example. And on the right-hand side you have the arguments, which is an array, and it might be empty as well. And then finally we have let definitions. So a let definition contains a variable name, then the value for that variable name, and finally the body. And within that body, the variable should be in scope. And there's a tag, of course. So tags have a name and then a list of expressions. And this representation is sometimes called an abstract syntax tree. And it's called abstract because it doesn't always necessarily map completely onto the concrete syntax. So the parentheses that you write and so on. So the abstract syntax means that it's already one step away from that concrete syntax. Okay, so recall we're going to write a parser, and what a parser does is it tries to take a string and constructs one of these expressions. So this is what our parsing function looks like. It's a function parse, and it returns an expression, and it might throw, and that's when we hit a parse error. And the first thing we do is we create a substring in the called remainder. We try to parse an expression on that remainder, so that's a mutating function on remainder. And then we make sure that the remainder is empty. Otherwise, we forgot to parse something, and that's an error. And finally, we return it. Now, so what does parse expression look like? Well, parse expression is built up out of smaller pieces, and the most essential piece is parse atom. And this is parsing something like a string literal, a number, a tag, or an identifier, a variable. And it does that by looking at the first character. So here we can see that there's a check if p equals first, and then we check whether that's a decimal digit. If yes, we're going to try parsing an integer. Then there's the case where we see a quotation character, and then we're going to try to parse a string literal. There is a case for an identifier, where we try to parse a variable, and a case for an angle bracket, where we try to parse a tag. And then we have the case where we do have a first character, but we don't recognize it, so we should throw an error in there. And finally, if we don't have a first character, we should also throw an error, because we do expect something to be there. So the case for integers is very simple. We just move the logic to parse int, out of which we get an integer, and then we wrap that in our integer literal case. And when we see a quotation mark, the first thing that we need to do is remove that quotation mark. And then we're going to try parsing everything we see until we hit another quotation mark. So that's this remove while. And then we expect that there's going to be another quotation mark. That's the end of the string, literal. And if it's not there, we're going to throw an error. So if it's not there, it typically means we're at the end of the file. So then we return a string literal. Now, if we see an identifier starting character, we're going to try parsing an identifier and return it as a variable. And parsing a tag is a little bit more complicated, so we create a separate method for that. And finally, if we don't recognize any of these things, we're going to throw an error. And this is the error expected atom. So that's an enum value, and we can write lots of these enum values, each for a very specific error. And then we can later on create nice readable error messages for that. If we don't have a first character, we will say that we unexpectedly hint the end of file. Now, parsing an integer is actually really simple. We just remove from the string, from the beginning of the string, while we see a decimal digit. And the context in which we call this is important. So we only call this when we check that the first character was a decimal digit. So that's why this is a safe method. So we remove, we know that there's going to be a non-zero amount of digits. We turn that into a string and turn that into an integer. And then out we get an integer. Parsing an identifier is a little bit more complicated, also because we're going to use this in multiple places. So here we first remove identifier characters from the beginning of the string. We then make sure that the identifier characters are not empty, so that we found at least one character, and then we return a string. Parsing a tag is a little bit more interesting because it's recursive. When we see a tag, the body might contain other expressions. And to show you what it looks like, when we write a tag, let's say title, that gets parsed as the tag title. So that's very simple. But if we want to write expressions in this, we're going to use a sort of JSX kind of language. So we don't want to be able to write something like the variable foo within the title, but we want to write that using curly braces. So that's what this looks like. That's the syntax. And now to parse that, the first thing we're going to check is whether we see an angle bracket or a curly brace. Otherwise, we're going to throw an error. And in the angle bracket case, we expect there to be optional white space and then the name of the tag. And we're going to reuse parse identifiers. So that just parses a bunch of letters. Then we expect the closing angle brackets. Otherwise, we throw an error. We again skip some white space, and then we're going to try building up this array of expressions. So while we don't see a closing tag, we're going to keep trying to parse an expression. And we recursively call ourselves. So this allows us to nest tags and nest multiple tags within a single tag. If we see a curly brace instead, then we skip some white space if it's there, and try parsing an expression, skip some more white space, and then we expect another curly brace. Otherwise, we throw an error. So this is how you can embed that recursion into your language. And it's just calling functions recursively. Now this is, I think, a very interesting part of it, throwing an error. And I think errors are super important, and that's one of the things that make building a language hard if you just start out with your first language, because you need to think about this from the beginning. Otherwise, you're going to program yourself into a corner and it's going to be hard to get out. So this parser has built-in errors, and you saw this a few times already where we said throw error. And the error function is basically a function that constructs a parse error. So what does it look like? Well, it constructs a parse array with the position and the reason. And this position is the current position in the substring. So I think it's called start index, but I think the name position is a bit clearer for what we're trying to do. And using that, you can then later on, when you receive a parse error, or when a function throws, you can reconstruct the exact position in the string where the error happened. Here's a few of the reasons that exist. So we have unexpected end of file and so on. And you can really make this as big as you want and later simplify it. It's probably, worst case, it's a bit better to be very precise than to later on not have to know what happened. Here's the code for parsing a function call. So the first thing that happens is a function call tries to parse an atom, and then if it sees an opening parenthesis, it will parse an argument list, and the arguments are separated by commas. And the reason why it first tries to parse an atom is so that we can nest these function calls. So if we switch to our parser, we can write something like foo and then call it with 5. And then let's say that this gives us another function. We can call that with hello. And here you can see how that gets parsed. So it's a function call of foo with the parameter 5, and then that gets nested inside another call with hello as a parameter. Now let's think about evaluation. So evaluation is taking this parsed tree and turning it into a value. So if we have a simple string, we want to evaluate this into a string value. And likewise, if we have an integer, we want to evaluate this into an integer value. If we have a tag, it's also very simple. We basically want to output again the value of the tag. So that is basically like a no-op almost. Now it gets interesting when we embed strings. So let's say we have a tag with a string embedded in there, hello. Now we want to evaluate this thing into HTML where we have a p tag and then hello inside. So let's see how that evaluates. To evaluate the p tag, the first thing that we need to do is evaluate this string. And then we get out the value hello, and then that gets used inside the p tag, and then we get the HTML out. And one cool thing is that we can embed, for example, things like angle brackets inside the string. And because we know the structure that's going on, we can do escaping right. So first we try to evaluate the p tag. In order to do that, we need to evaluate the string, and then we get a string with angle brackets, so no escaping. But the moment we try to use that string within a tag, it gets escaped. Another interesting case is when we try to evaluate a let expression. So a let expression, in order to evaluate, the first thing we need to do is evaluate the value. So if we say x equals 5, we need to evaluate that 5 node. So that gives us 5, and then we need to evaluate the body of the let expression. So that's where we can use that value. And to make it a little bit more interesting, of course, let's x equals 5 in x. Here we evaluate the value 5. We then evaluate the body, and within that body we can use x. And then out we get the value of 5. And another interesting case is evaluating function expressions. So let's say we do something like x equals func ab, and then the body b in x, and then we call x with 1 and 2. So when we evaluate this, we first have to evaluate the let expression, and then we hit a function. And we cannot evaluate the body of that function because we don't have the parameters yet. So the only thing we can do is return that function as a value. And then we can evaluate the call expression in the body, and we resolve the variable x, which returns that function. We evaluate each of the parameters, so 1 and 2, and then we can call the function. And then, only then, the body gets executed with that b in scope. And then we can that gives us the result 2, and we can propagate that up, and then the entire thing evaluates to 2. So you can really see how this evaluation is built up out of simple rules. There's one rule for each node in the tree. And that's exactly what the evaluation function looks like. So when we want to run an expression, we return a value. And we do that by calling evaluate on the evaluation context. And a value is either a string, HTML, an integer, or a function value, which has to be evaluated later on. And to evaluate an expression, we need to do that within a context. And a context basically is a mapping of strings to values, so of variable names to values. And you start out typically with an empty context with no variables in scope. And then, for example, once you hit a let expression, you put that variable in scope for the body. So evaluate can be implemented by writing a switch over expression and then implementing each of the cases. So in case of an integer literal, we simply return that int. In case of a string literal, we simply return that string. When we see a variable, we look it up in the context and we expect it to be there. If it's not there, we throw an evaluation error. And this is an untyped language, so we don't really know whether a variable is going to be in the context when we start evaluating things. In a typed language, with a type checker, you might be able to remove this check. When we see a function, there's nothing we can do. We can only return a function value. And this is an interesting case where we see a let definition. So when we see a let definition, for example, x equals some expression, the first thing we need to do is evaluate that expression. So that's the evaluate value. Then we clone the current context by saying nested context equals self, and we add the value of that evaluated expression to the context. And then we evaluate the body with the new context that contains our variable. If the variable was already in the context, we simply override it. Evaluating a call expression is a little bit more work. So let's do it line by line. The first thing we do is we evaluate the left-hand side. So typically when you write foo and then parentheses open, it's foo. And at some point we might have complicated expressions. Currently, I think the only thing that makes sense is to have a variable there, but we allow for any expression to be there. So we evaluate that expression, and that needs to be a function. So if it's not a function, we cannot call it. So that's where we throw an evaluation error. The next step we do is checking that the parameter count matches. Otherwise, we throw an evaluation error. And in the sample code that I'll put online, you'll see that we actually have slightly more verbose error messages where we also say how many arguments were expected and how many they got, but that doesn't fit on the slides. Then we evaluate each of the parameters recursively within the current context, and then we finally create a nested context for the body of the function. And in this nested context, we simply put each parameter in there with the right name, and we evaluate the body within that nested context. Evaluating a tag is a little bit similar. So we start by creating a string with the opening tag. Then we loop over the body and we evaluate each body element. And if we see HTML, we can simply append it because we're already sort of inside HTML. If we see a string, then we escape it. So this makes sure that the escaping goes right and that the user of our language cannot make mistakes. If we see anything else, for example, an integer or maybe later on arrays or dictionaries, we throw an error. And finally, we append a closing tag and we return the value as HTML. So we can see from here that we can already build quite complicated expressions. So let's say t equals title, and then, well, actually, let's make a function for this. Let head equals the head tag, and then put that inside a function that still takes the name. And we have a title tag in here, and there we can use the name. We can close the title tag, close head. And and then we write in, and then we call head with UIKonf, and this will really already evaluate the entire thing. So it calls the head variable, then tries to evaluate UIKonf, then calls the head function by recursively calling the body, and with each step the HTML gets bigger. And then once we're done, this evaluates to head title UIKonf title. And for a basic language, most of the important things are covered already. A lot of the other stuff is work, but it's syntactic sugar, and similar to how you would implement this. Before I said that error messages are very important, and we throw the right error messages when we parse a string and we cannot recognize it. But what if we hit an error message during evaluation, for example, a variable missing? We threw an error there, but it doesn't know about the position. So for a single line program, that's fine, of course, maybe. But the moment you have slightly more complex things, you want to know where something went wrong, and not just get an error. And doing that is a bit more work. So here we have our expression enum, and in this expression enum, we basically threw away all the information of where the expression comes from. And to add this, we need to annotate the expressions. And one thing we could do is to each case, we could add a source range, like let's say the start position and the end position of that expression. But that becomes very tedious. Instead, we can use a small trick, and we can focus on recursive parts of the expression. So over here. So if we take those recursive parts and replace it with a generic, that allows us to annotate our expression with any kind of annotation we like. So we could do, for example, this. We could create an annotated expression with a range, and then inside we have an expression of annotated expression. So this is a little bit mind-bending, but it's really useful to annotate, to make sure every expression is annotated without having to rewrite it every single time. And you can create different variants of this as well. So in our tests, we also have a simple expression, which is exactly the same thing without the annotation, and then you can easily map between the two. So these are, at least I think, the two most important parts of building a small interpreted language. You need to parse that language and evaluate it. And there are many, many different ways to do this, but I figured like showing a way to do this in plain Swift without the use of any external libraries would be helpful. And I don't think everybody should now try and build their own programming language to get world domination. It would be super cool, of course, if you're inspired to do that, but I don't imagine that will work. But I do think this can be very useful within your own apps during prototyping, for example, or when you're writing, let's say you're writing a 3D modeling app and you want a user to express these 3D models as a program. That could be useful. Let's say you want to build a small console into your app, like your game or whatever kind of app you have. You can parse and evaluate an expression language there. Or let's say you want to build an app for making websites, you could embed a template language in there. So there are a lot of challenges still remaining. If you want to have fun with this, you can take the code from GitHub and try to add some more features. You could, for example, implement a type checker, which sounds, or even a type inferencer, which sounds super complicated, but once you've done it, it's doable. It's actually very interesting and lots of fun, and it's not that much code. It takes a long time, at least it took me a long time to understand it, but it's very doable. You can add more features like for loops, or if conditions to the language, or other data types like arrays and dictionaries, and You can also do all these things at the same time or after each other in whichever order you prefer. You can write nice GUIs like we saw now for evaluation and for debugging and for highlighting and syntax highlighting. There's one big thing missing. I would say that's really almost a design flaw. So currently our parser, it does give very good error messages, but then it stops. So remember that we threw errors once we hit an error case. And in a real programming language, you probably want to continue parsing. So we don't do that. We throw an error, and imagine that Swift would do the same as we do here. That would mean that probably Swift could only highlight up until the point where you made an error, and then everything after would be black or gray. So that's not very good. So in a real implementation, you probably want to continue parsing and try to repair that error and at least highlight all the other parts to the user. But that's maybe for a future talk. Thank you.